Awesome. Okay, now, guys, today we are planning to start with the new chapter of the book. And the new chapter of the book is essentially, it's going to be very easy, although the thing that we cover is going to be a little bit different from the things that we have done in the past. And now we are trying to solve a trigonometric identity today and tomorrow. And we finish it these 2 days, and from Tuesday next week, which we have almost a week left before the final exam, we see your, I should say, presentations. We do some kind of a new stuff, not as much as we can because we are almost done, and also get prepared for the final exam, which it's gonna happen on May 27th. I'm just gonna confirm the dates with you, but probably the final exam which we're gonna have, it's gonna be the same time, 11:10 on, I should say, May 27th, most probably. Let's see. Okay, now the topic that we're going to cover is essentially today, that's the thing, almost the same thing that we covered so far in the trigonometric functions, and particularly the concepts that you solved that yesterday on your diagnostic test, which was the inverse of a trigonometric function. But as a general rule, we just want to define today what is a trigonometric function. Then we come to find two methods to solve those functions. The methods that we're going to solve about them, it's in two different categories. The first method, give me 1 second to pin the video there. Okay, it's not fine. The first method of solving a trigonometric function is going to be the analytic approach, and the second method is going to be the geometric approach, which we just want to follow both of them. Please listen to today's lessons very carefully, because this type of functions arises in most of the applications that you have to solve an equation, which they involve a trigonometric ratio of a single variable. Okay. Now, in order to explain the whole concept, I'm just gonna solve one example for you, and a very basic example for you. Then we move on step by step with more advanced the concepts in the trigonometric ratio. The first example that we just want to solve is this. We say that, for example, 2 times of square root of number, let's say, pi, it's equal, the sign, let me change the paper. 2 times of square root of pi times sine x equals to what? Equals to the same thing. Let's call that the same thing. Square root of pi. Okay, guys. This is going to be the first easiest trigonometric function that we are just going to cover that today, and let's see how we can solve it. Everyone can see what I have written there, huh?
Yes.
Yes? Awesome. Okay, and now look at this. The thing that we have is this. We say that, okay, it's going to be the sine of the x. But look at this one. This equation, this is an equation because we have an equality and we have the x. But what's the problem with this is that the x that we have as our unknown variable, it's confined, is trapped by the area of a sine function. You see the sine attacked the x and got us down to that. Then it's not as the functions that we had in the past. For example, we say that 2 square root of pi x equals to, let's say, square root of pi. Becomes very easy. But because we have this sign of x attacking to the x, then as a result, we see that because of that, we cannot solve this equation as what we did before. And now that's why we call that a trigonometric equation, because our single random variable is attacked and got stuck by the sign. And now it means that we have to search for new methods in order to find what is the value of the x. Because the goal that we are going to have for these type of functions, the goal that we have is to find a value for the x. And that's the plan which we have. Okay, in order to solve this equation, we follow the same principles that we have done in the past. What do I mean? We mean that as, for example, the thing that we did in the past, and we say that we have to isolate the x on one side of the equation and write all known variables to the other side of the equation, we are going to do what? We are going to come here, do the same thing. I say that I'm just going to divide both sides of the equation by 2 times square root of pi. Then what's going to happen? Then I would end up with what? I would end up with this expression, that the sign of the x should equal to 1 over 2. You see that I have square root of the pi on both sides of the equation. Then if I divide both sides by 2 times of the square root of pi, then you see that these square root of pi are gone. And I have ended up with only 2 at the denominator of this expression. Then I have sine x equals to 1 over 2. So far, I did a great job because I was able to isolate the trigonometric ratio on one side of the equality and keep the other non-variable to the other side. But I'm not so much satisfied because the thing which I remember I have done in the past, I was able to isolate the x on one side of the equation and all the other variables to the right. Now I have the sign which is glued like stuck to the x, and I have to get rid of the sign itself. Then I can say, okay, the perspective for me is that then I can have x only expressed in terms of the other sides, other variables, but it's isolated with coefficient 1, not in this format. And the strategy which I have to follow is this. Then I have to come with a strategy to get rid of the sign on one side of my equality. What can I do? I'm only going to draw your attention to one of the things which we learned in the past. We saw that previously, that if I have sine inverse of sine x, it gives me a variable x. We saw that before. We saw that we can just use, that's a kind of a property, not only of the sine x, of any function composition with its own inverse function, which it gives the whole argument to come outside. It's not only for the sine, you learn that it's going to be a general property of any function with its own inverse. When both of them get composed into each other, then you can just extract the argument, which is x, outside. I'm just going to use that property, which we've worked on that yesterday, to take inverse sine from both sides of this, I should say, function, because I know that if I do that, I can rely on this identity, then extract x out of it. Then it means what? Then it means that I can just come here. I can write what? I can get sine inverse of sine x equals to what? Sine inverse of what? 1 over 2. Everyone is okay so far?
Yes.
Yes. How about Philip and Ferris?
그래.
Good. Then, guys, look at that. I was able now to construct the same thing that I talked about that before. Now, on the left side, what do I have? I have sine inverse of the sine of the x, which I know based on the things that we have practiced so far, I know that this argument, it gives only the x. On the right, left should be equal to sine inverse of 1 over 2. Then actually I'm getting much happier right now because when I look at this, I feel much more relaxed, much more at ease. Then I say, okay, the functions which I created here, it essentially expresses my x in terms of something which I know about that. It's a quantity 1 over 2. It's not another unknown identity, an unknown quantity. Then I'm almost half smiling because I was able now to extract x completely on one side of the equation. You see, I have only x expressed on one side and isolated with coefficient 1 and power 1 in terms of something. But the question is that, then if I say x is inverse of sine of 1 over 2, I'm talking inversely, I'm talking backwards. For example, imagine that when we talk about the inverse of the sine of 1 over 2 is like, for example, I'm just gonna pick one name from you, the easiest name to just reverse it. For example, look at that. For example, Rose. Rose, look at that. For example, your name. Your name is R-O-S-E. Huh? Or look at my name. My name is Omid, O-M-I-D. If I call my name, it becomes Demo. Backward. If you call me Demo, I do not just respond to you because I do not understand what are you talking about. Huh? Then, but if I call me Omid, the forward of my name, I understand. That's the same principle with the inverse function. When you call them inverse of the sign, it's like you call me Demo. You inverse my name, you say Omid, it becomes Demo, then what is that? Then I do not understand it. Then it's because this one, then I have to put that in the forward. I have to name it in a forward. It's Demo now, I want to call this Omid. Then the best way to do that is this. I come and I say, what is the angle in order to answer that question? What is the angle that its sine becomes 1 over 2? That's, if I ask that question like that, it's essentially I'm asking it in a forward way and I'm calling this function in a forward way. Like my name, you do not call me Demo by this way. You call me Omid and I can respond back to you, say, what? Do you need anything? And guys, instead of I write x equals to inverse of the sine of 1 over 2, I ask what is the sine, what is the angle that its sine becomes 1 over 2? What is that angle?
Pi over 6.
That's right, pi over 6. And Philip and Ferris, if you are wondering why this is pi over 6, please remember these are the, I should say these are the reference angle. Pi over 4, pi over 3, pi over 6. Please write this trigonometric function of these three angles and place it somewhere on your desk. Because I do the same thing myself. I cannot memorize them all the time. I have it somewhere handy. And you see that by doing this, I solve the equation. Then I can say x should be equal to pi over 6. But I want to show you something more before I tell you that's going to be the final answer. Okay, so far, everyone agrees at this stage and everyone is happy now and okay that x based on the thing that we did, x can be pi over 6 or 30 degrees then. Everyone is okay so far?
Yes.
Yes. How about Philip and Ferris?
Yes, sir.
No questions, huh? Okay.
No question.
Awesome. Glad to hear it. And now, this problem, guys, is not yet fully down. You have to do something extra to that. And before I do that, I just open one part of this square empty. I go back to this in a couple of seconds in order to solve this equation. But before that, I'm just going to warm up your brain with one interesting fact. Look at that. Okay. And now, look at that. I say that, for example, sometimes we have, let's say, we have two functions. I call it y equals f of x. And I have another function y, which is equals to g of x. They can take any form. F of x can be anything, g of x can be anything. But the thing which is common between them is that both of them are single variable functions, f and g. There's only one variable x. Guys, you know that if I say, okay, I have these two functions, and I come here, I say, I call this y1, I say this y2, I say I take y1 should be equal to y2. I say that their y should be the same. For example, if y1 function of f of x represents, for example, let's say, for example, my salary, y2 represents g of x, represents a function which expresses the salary of Dr., for example, X, which teaches at the school. Okay. Then when I say y1 equals to y2, what do I mean? I'm looking for a point, the time of the year, that my salary and Dr. X is gonna be exactly the same thing. We get the same income from teaching at this school, at this college then. Does it make sense to everyone? That what do I mean if I put y1 equals to y2?
Yes.
Yeah? It means that if y1 and y2 represent salary of two persons, when you put them equal, it gives you the time of the year that this salary should be the same. If I get, for example, let's say, for example, $20 per day, it gives me the other professor the $20, the other teacher $20 that he gets at the time of the day. By doing this, essentially, what do we do? By saying this, we say that, okay, I can say, if I'm looking for this, I can come here and say, okay, f of x equals to g of x has the same meaning, correct? If you say y1 equals to y2, it's the same thing if you say f of x equals to g of x, correct? And they are the same thing. But it means that when you solve this equation, you get the x's that equals my salary with that person. Now, imagine you want to do something extra. You say, okay, I'm not going to solve this equation. I hate solving the equations. I'm just going to go to my Desmos or any graphing calculator and plot this function. I'm going to have a random plots for this function. For example, for f of x, the function looks like that. For g of x, the function looks like that. It's going to be g of x. It's going to be f of x. And now, look at this. For both of these functions, there is a point that these functions are colliding, that these functions hit each other, and they call that intersect. You see this point, guys? I call that point, for example, x naught. You see, for this point, it means that these two functions They have something in common. For example, one of them is girl, one of them is boy. They have one characteristic in common and they decided to marry, to get married. It's going to be x naught on the x. It's going to be y naught in the x. It means that at this point x naught, these two functions intersect. Then these two functions are equal to one value. Does it make sense to everyone?
Yes.
Yes? Philip and Ferris?
Yes.
Awesome. Then it means that when I want to solve an equation, when I'm looking for the x, which is a common thing between them, for example, imagine f of x is the husband, g of x is the wife. They are going to get married. When you equal them to each other, it means that the husband and wife, they should have something in common. For example, both of them are so happy. Both of them are tall. Both of them are, for example, have black hair. Both of them, they have green eyes. When you equate them to each other, you are looking for these common points. When you plot them, the intersection shows you those common points. And that's essentially what do we mean by equating two functions. You're looking for the x's which are common between them, like a husband and the wife who have both green eyes. By saying that, I go back again. Any questions so far? Everything is fine? By saying that, I go back to the same problem which I had before. By saying that, I go back to the same problem which I had before. And for this, I say, okay, now imagine I had two functions. Imagine that the functions which I had, 2 pi of sine x equals to the square root of pi. When I divided both sides by 2 times the square root of the pi, I end up with this equation. Look at this. I ended up with this equation. Then I tried to solve this equation. I started analytic job from this part. Look at this. From here to get there and to get there and to get there, I use analytical solution because I took the inverse transformation, then I moved back to the forward transformation. It was you moved inverse, then you move back forward. And that's essentially the thing which we did from here. But I say I'm not going to do the analytic solution. I'm just going to start from this and do the geometric solution. What do I mean? I mean that you look at this function as f of x, and you look at this function as g of x. Sine of x becomes your f, g of x becomes 1 over 2. Then you plot them, then you see the point that they are intersecting, that they are just cross each other. It becomes the thing that it's common between them as a wife and husband, and it becomes my solution as pi over 6. Does it make sense, guys, what I'm going to do?
Yes.
Philip and Ferris?
Yes.
Okay. And now, guys, I'm going to share my Desmos with you. But before I share my Desmos with you, remember, the solution that we got for this equation, analytic part, it gave me the solution as pi over 6. Okay. And now, I'm going to share my Desmos with you. I'm going to share my screen. Anyone sees my screen?
Yes.
Let me remove them. Okay. The first function which I had, as I called it, let's call that the husband. Husband was what? Was equal to sine x, correct? And the other function which I had, it was the wife that she was getting married to, y equals to sine x. What was that? It was 1 divided by 2. When I say that, sine x equals to 1 over 2 equals to 1 over 2, it means that I'm getting married, this sine x and 1 over 2 as a husband and wife, they are getting married. I'm looking for the points which is common between them, which geometrically, it becomes the points that they are intersecting, that they are crossing each other. And now look at this. Guys, the blue line, the blue curve is the sine x, but the green curve is what? Is 1 over 2. You see 1 over 2 is 0.5. And look at the first point which they intersect. If I walk from left to right, from 0 on the x-axis, I'm moving to 1 over 0.5. I see, look at this. They are intersecting. You see this point, which is dotted by gray. And I click on it, it gives a coordinate. What is the x-coordinate of that point, the intersection?
Pi over 6.
Pi over 6. What was my analytical solution?
Pi over 6.
You see, I ended up with the same answer. Pi over 6. From the analytic solution, that I had to just inverse the function, then again move forward from the function, transform it back again to the same thing, it gives me pi over 6. And the geometry representation also, it gives me pi over 6. But look at this, look at this. There's another point of intersection. You see that? I have, what is the coordinates of the second intersection?
5 pi over 6.
That's so true. And now let me do this. I have pi over 6. I have 5 pi over 6. Look at this. I have 13 pi over 6. Now I have 17 pi over 6. Now I can just zoom out. You see, I have lots of intersection points. You see that, guys? Pi over 6, 5 pi over 6, 13 pi over 6, 17 pi over 6. I can move back. I have minus 7 pi over 6. I have minus 11 pi over 6. You see, I have many points. I have infinite number of the points, essentially, which this is common between the husband and wife. You see that? The husband, if this is sine of the x, and the wife, if this is 1 over 2, they do not have one point common between them. They have infinite number of the points which is common between them. Both of them are, for example, are tall. Both of them have green eyes. Both of them, they have blonde hair. Both of them have, for example, the same shoe size. You see, then the solution of that question which we have, it's not only pi over 6. It is infinite number of the solutions. You see that? But now, look at this one. Give me 1 second. Okay. Okay, guys, any questions?
Oh,
No? Okay, let me stop sharing and go back to the same, I should say, thing that I had. Guys, look at this. With the analytic solution, I got pi over 6. With the geometric solution, I also got pi over 6. But the problem was that the geometric solution, as you saw, it gives infinite number of the solution. then it means that the analytic solution didn't give me as many as common points as I got it from the geometric solution. And in order to compensate for it, you can say that always you can come here to add the periodicity of the sine function, which it becomes 2 pi, but with a constant, let's call that, let's say k, which k becomes 0, plus minus 1, plus minus 2, and goes on. Then it means that with the analytic solution which you got, you can always add it or subtract it from a periodic term, which is 2 pi for the sine, but always you can multiply that by something different. Look at this. It's 2 chi pi. It's the periodic behavior of the sine function. Then it means that when you get the analytic solution, always you can add many terms. For example, you can have k equal to 1. You say the solution becomes pi over 6 plus 2 pi. You can have k equal to 2. You have pi over 6 plus 2 pi. And that's essentially a very beautiful property of the trigonometric function. They do not stop anywhere. They have periodic behavior. They move on forever. You can keep counting up the solution of this function until you get, let's say, on the next 100 years, you can keep finding solutions for this equation. But we always look for the first solution, which is between 0 to 2 pi. We say that on one round of the circle, unit circle, the solution is going to be confined there. And you can get every answer from the first part of the solution there. Okay. Guys, any questions?
No.
No, everything is clear.
Yes.
How about Philip and Ferris?
Yes.
Okay, now, you know that, guys, when you do not have the questions, it's my turn to ask you questions. I'm going to give you one question to solve. You also please follow the same things that I did, the geometric approach, analytical approach, and try to solve it. I have for this equation, I have 2 times cosine of the x plus square root of 2 equals to 0. Okay, guys, I give you 5 minutes, I think should be fine, to try to see if you can do the same thing which I did, both from analytic and geometric approach. Then we share our result in 5 minutes. Good? You see what I have written there?
Yes.
Good. 2 times cosine x plus the square root of 2 equals to 0. And guys, please, whenever you're done, let me know. Guys, are you done?
Yes.
Okay, what was your answer?
It's 3 pi over 4.
Huh?
At 3 pi over 4.
Okay, that sounds almost correct. And how about Philip and Ferris?
I'm okay.
Huh?
Just wait a minute.
Yeah, sure. Okay, I'm just gonna solve it, and in case Philip and Ferris have not fully done with that, we are just please help me and follow the things that we can do. Guys, look at this. For this one, again, the simple strategy and approach, it's gonna be what? It's gonna be that I just take this one to the other side and isolate the cosine x, which it takes you to this expression that cosine of the x should be equal to square root of 2 minus square root of 2 divided by 2, correct? Then you may end up to have two kind of solutions for it. The first kind of solutions that you may end up with this is that you say that, okay, I'm just gonna go inverse it, move backwards, transform it backwards, and I say that cosine inverse of cosine of x becomes equal to cosine inverse of Everybody sees the color which I'm using?
Yes.
Okay, glad. Square root of 2 minus 2 divided by 2. Then you see, wow, I see something very interesting. And I see something incredibly interesting. And that's going to be this, that the cosine and inverse of the cosine, they are essentially from the same nature, which it takes you to this point that cosine inverse of the cosine becomes what? Becomes essentially the x. And this one becomes what? Becomes cosine inverse of this expression. Minus square root of 2 divided by 2. And now, you know that wherever you are at this stage, always the best way to solve these equations is that you are going to ask yourself the direct transform. You transform it backwards again. You come to the direct transformation of the cosine, and you say, what is the angle that its cosine equals to square root of 2 divided by 2 minus essentially. We have this square here, which means we have to fill this out. Okay. What is this angle? That its cosine transformation, it gives you the numerical value as minus the square root of 2 divided by 2. You may think to yourself, I know, wait a minute, it's somehow similar to those reference angles that we talked. Isn't that going to be pi over 4? Guys, are you here with me? We had before that the cosine of pi over pi, the cosine of pi divided by 4 equals to plus square root of 2 divided by 2. But now we have this one minus square root of 2 divided by 2. Then what's that going to be? I'm just going to just very quickly show you something that we had before on this one. And we said what? We said previously on, it's a kind of a digression of the things that we learned. I'm just going to do some kind of, I should say, unit circle. You may not probably see that, but look at this. These points, the intersection, it shows the intersection of my unit circle with this axis. Look at this. I'm just going to plot an angle at point P. P stands for point, which picks, I should say, the angle, let's call that alpha. You see this, guys, that when you talked about the cosine, we said that the cosine, it's the normal projection of your points of the circumference on the x-axis. Then we said that on the unit circle, we call the x as the cosine. If P is x and y, we said that the cosine of alpha equals to x. X is going to be the distance between the normal and the origin. We see that, guys, also, if you want to get the same thing, to get this because of the symmetry which is introduced by this circle, we can end up with the same thing and say that, okay, I can get the same x if I'm going to be here. You see that the P prime here gets x, but minus y. You remember the things which we talked before. But if I want to get my point minus x as its, let's say, at its cosine, I had to sign it and I had to make an angle like this, and my angle points this one all the way up there, and this one becomes the cosine because that's the normal to the x, and this is minus x. I hope that you remember it. We had the point, for example, P, which is minus x minus y. But the angle which I collected here, which the angle is starts from here all the way goes to there, it becomes how much? 2 pi plus alpha. Then it means that the cosine, if the cosine of alpha is x, the cosine of alpha plus 2 pi becomes minus x. That was a thing that we talked about the symmetry, I should say, many sessions ago. And I hope that you remember it. Then it means that if I go back to the same thing which I did, which it was, I should say, and now the cosine of what angle becomes minus the square root of 2 divided by 2. If we know that the cosine of pi over 4 is the plus sign of this, then this angle becomes what? Becomes what? 2 pi plus pi over 4, which becomes how much? Nine pi over 4, huh? Guys, are you, do you have any problems? Do you have any questions so far? Did I go too fast?
No.
Everything is fine?
Yes.
Okay. And now, one of the things that we can do before everyone is okay with the thing that we talked about there?
Yes.
Yeah? And also, before I go to this one, I just want to, it was one more drastic. Also, you can find another angle in case if you have done it. Let me choose one more color. You can get the same thing if you remember from the symmetries. You find another point here, the symmetry, and this one also shows you the same cosine minus x. And this point also, P, it gives you, let's say, minus x, but the point y. You see that also cosine of, which this angle becomes what? This angle to get to this point P becomes pi minus alpha, huh? We saw that the cosine of pi minus alpha also, it gives you minus x. Please review the things back, which we covered that in many sessions ago on the very first lessons of this trigonometric ratio, and we talked about these 4 points relation to each other because of the symmetry which is introduced by the circle. Then it means that this point also gives minus x. Then I can just say, okay, pi minus alpha, which here it becomes pi minus pi over 4, which becomes how much? Becomes 3 pi over 4. Any questions, guys?
No.
And now, before we go for the break, I'm going to show you something. Before we go for the break, Philippe and Ferris, are you okay? Do you have any questions or everything is fine?
Actually, like I have many questions for this.
What is the first one?
First one, let me think. No, it's actually it's not the first one. It's the how do you say that? It's I think I can understand it by myself.
You say what?
I said I can understand it by myself.
Oh, you mean you can, huh?
Yes.
Okay, if you can, please do that and also watch the video. In 2 minutes, we are going for the break. If you do mind, Faris, try to do if you can produce the same thing. If you cannot, then we come back from the break, ask me your questions, okay?
Okay.
Awesome. But before we go for the break, we want to do the geometric representation. And for do the presentation, please everyone open your Desmos. I'm going to do the same thing. I'm just going to plot these two functions, guys. Look at that. I'm going to do a kind of a geometric representation. And this time, before I do the geometric representation, I say, okay, I had these two functions, which from here, essentially, as you will see, my analytic solution guys, as you will see, starts from this step, huh? From this step, that cosine x equals to minus the square root of 2 divided by 2, I move to just take it transform inverse, then move it back again to the forward representation. From here, I say I don't want to do that. I want to do the geometric representation. Then I'm just going to look at the cosine x as a husband and y equals to minus the square root of 2 divided by 2 as a wife. Then I'm just going to plot them to see how many common points do they have. The first common points is going to be, I should say, the answer to my question. Okay. What was this one? It was cosine x minus the square root. Okay. Guys, look at that. The first one becomes y equals to cosine x. We are going to go to the break. Don't worry if you're tired. We are going to go there in less than 1 minute. And the other function, which it was the y, it was minus square root. For square root, I write sqrt 2 divided by 2. Look at this. The blue plot is the cosine. The black line is the minus the square root of 2 divided by 2. Look at the first connecting, the first intersect. What is the x-coordinate of that?
3 pi over 4.
That's right. How much was r, the first coordinate, which you found analytically? Analytically, how much did we get?
3 pi over 4.
That's right. You see, you always, it doesn't matter which method you use, but always you get the same common points between the husband and the wife, which is going to be two equations which we had. Look at the next intersection. 5 pi over 4. The previous one, minus 3 pi over 4. You see, there are many points, not only one roots. You have many roots, 3 pi over 4, 5 pi over 4, 11 pi over 4. You see, minus 13 pi over 4. You have minus 3 pi over 4, minus pi over 4, and it goes on. You see that when we have many, many solutions. Then how to deal with that? In the analytical part, we have only one solution we obtained. But in order to remove that discrepancy between the analytical solution and the thing that we did, geometric, always we add plus 2k pi, which k can become 0, can become plus or minus 1, can become plus or minus 2. Which, as you notice also from before, this part, 2 pi over 4, it shows the periodic behavior of the cosine function. with any cosine and sine function, because you learned every 2 pi represents one full circle on the unit circle. It means that any 2 pi, the function behaves, copies itself. For example, if the function laughs, at every 2 pi, it laughs again. If it's crying, after 2 pi it passes, it starts crying again. It repeats itself. And that's how, by adding this term, we reconcile the geometric representation with the analytic representation of solving a trigonometric equation. Any questions, guys?
No.
No, everybody's fine? Philip and Ferris?
Yes.
Yeah, please, fellas, in the meantime that we're going to go for the break, please take a look again on this. And if you didn't find anything that it's going to make sense, please, when you come back from the break, ask me in the class then, okay?
Okay.
Fantastic, fantastic. The time is, I should say, 12:20. Let's take a quick break. And please come back by 12:35 then. Is it good? 15 minutes break. Awesome. I see you guys in 15 minutes in 12:35 then. Enjoy your break time. Stop recording. I'm just gonna put my laptop upside down. Okay, now we solve one question. Okay, now we solved one question, guys. Now what's the time for? Guess what is the time for now? Another question to solve. Okay, we have still enough time. If you give me 1 second. Okay, let me give you one more example. The example we're just going to work with that, guys. It's very interesting because it's going to be this. We are going to talk about the tangent squared of the x minus 1. We said that it's equal to 0. Okay. Okay, now. Okay, let's deal with this equation now then. We have tangent. Guys, everyone can see what I have written there? Tangent squared of the x minus 1 equals to 0. Is it clear for everyone?
Yes.
Awesome. Okay, now, for this one, you see that, for example, I'm just going to talk about something. We had, for example, I'm just going to review on something essentially. That's something that we have done that many times in the past. And we said that if we had a function that, let's say, for example, if this is x squared minus 1 equals to 0, it's the algebraic counterpart of this equation which we have. If we have x squared minus 1 equals to 0, in order to solve this equation, what did we do before? We said that in order to solve this equation, the thing that we do is this. We come here and we say that it becomes like that. We say that x squared should equal to plus 1. I take minus 1 to the right side and I change its sign to the plus. Then when it becomes this, then I came to a conclusion that x gets two values, plus and minus 1, because plus 1 squared becomes 1, and quite surprisingly also minus 1 squared becomes 1. And that's the thing that we did, that I should say many sessions ago, many years ago I should say, when we just started to work with the equations. Then we saw that for x squared minus 1, we can find two principal roots, which is either plus or minus 1. Okay, now for this one, we do the same thing. We have the tangent squared of the x minus 1. And in order to solve it, what should we do? In order to solve it, we do this. We say that we come here, we say that the tangent squared of the x equals to 1, equals to plus 1. Okay, and if I'm now there, I can just expand this one. Not expand, essentially, extend the knowledge which I have for this one from the things which I knew from x squared equals to 1 to have two different equations. And you see that for this simple one, we get these two. We say that, okay, it's going to be this one. Then I have two equations to solve. The first equation, it gives me what? Because look at this one. I had x squared equals to 1. I had x equals to plus or minus 1. And the same thing, it means that if tangent x squared of the x equals to 1, I can have either the tangent of the x should be equal to 1. And at the same time, not at the same time, or the tangent of the x should be equal to minus 1. Because either this one or that one, if you square them, you get to this one, becomes 1. Does it make sense to everyone?
Yes.
Everyone is happy? Happy? Yeah? Okay. And now, guys, look at this. What else I'm going to do? What else I'm going to do is this. I come here and I say that, okay, instead of solving one equation, now I have two equations. It seems that tangent squared of the x equals to 1 was inside the bag. You open the bag and you see instead of 1, you have 2 to solve it. Because we have to find the x, not the tangent of the x. Then you see that I have two equations to solve. In order to solve it, I'm going to go to the next page, do one by one. I'm going to start from this one, from the tangent of the x equals to 1. Then as you will see, we have two functions to solve it. The first function which we're going to solve is this. We say that the tangent of the x equals to positive 1. In order to solve it, I'm going to do the same thing, the analytic approach. Based on the things that you learned before, I'm going to say I take the inverse of tangents from both sides. What it means, it becomes tangent inverse of tangent x should equal to tangent inverse of plus 1. Everyone is good so far?
Yes.
No questions? Okay, now guys, look at this now. What do we have? We have the tangent inverse, tangent x. We have these two are essentially from the same nature. It means that we composed one function with its own inverse, which always gives us the argument of that function. Our argument here is going to be the x. It means that from this, we simply can write x equals to what? Equals to tangent inverse of 1. In order to see that, we are finding ourselves, we are facing ourselves with something which it has an inverse in trigonometric. It's like, for example, you call my name, instead of calling me Omid, you call me Demo. I do not respond to you because I do not understand how you're talking to me. You have to reverse me back to call me Omid. I'm going to do the same thing with this. I'm going to say, what is the angle that its tangent it becomes 1. Now it's better. I ask myself, what is the angle that is tangent equals to 1?
Pi over 4.
That's so true. It's going to be pi over 4. Thank you, Rose. Because based on the reference angle, which we learned that before, pi over 4, I can fill this inside this. The tangent of pi over 4, it's always 1. It's a reference angle. You remember pi over 6, pi over 4, and pi over 3, they are reference angles. It means that we know whatsoever we need about the trigonometry of these angles. That's why we call them reference angles. It means that we know everything about them. We know what is their sine, what is their cosine, what is their tangent, what is their cotangent, what is their secant, what is their cosecant. And that's the thing. And now, what we do, then it becomes apparent that x should equal to what? Equals to pi over 4 and if you do the geometric interpretation, you will see that there are many points. You please do that later. Then you will see that every point you can add to this the periodic pattern of the tangent, which is going to be, I should say, I'm going to write it as k. K can be any number times pi, which it gives you all the numbers at the same time. I'm going to write this. It becomes our first sets of solution for these inverse trigonometric functions. And this part, k can be any number. K can be 0, plus minus 1, plus minus 2, goes on. That's why you get infinite number of the solutions for this function. Any questions, guys?
No.
Everyone is fine?
Yes.
Awesome. And now, I go back to the page. For this equation, I solved only the first equation, which is going to be the tangent of the x equal to 1, which I got the solution for it as what? As x equals to pi over 4 plus k pi. K is a number. You know that it's going to be anything. 0, plus or minus 1, plus or minus 2. Now, I have the second equation I have to solve. Because the tangent is square root of the x equals to 1, it gave me one pairs of equation. Now, on the next page, I'm going to solve this equation. What do I get? I have tangent of the x equals to minus 1. Okay, for this one, the same thing. You say that my strategy is going to be as before. I'm going to inverse it to, let's say, for example, to take the inverse from both sides of it, and I write it like that. I say that, for example, the tangent inverse of the tangent x should be equal to tangent inverse of minus 1. And you see that, okay, this is the same composition of the same function with its own inverse, tangent and tangent inverse, which it gives me what? Which it gives me the argument itself, which becomes the x should equal to tangent inverse of minus 1. And now, I'm going to do the same thing. I'm going to answer myself a forward question, that what is the angle that its tangent in a box, that its tangent gives me what? Minus 1. And I ask myself that forward question. Is any questions up to this point?
No.
No? Philip and Ferris?
No.
Okay, thanks. And guys, look at that. In order to answer this, we saw that previously, that the tangent of pi over 4, it gives you number 1. But now we have minus 1. Again, you can go back to the symmetric, I should say, circle, which we talked about. If the tangent of the tangent we learned yesterday, that the tangent is going to be what? The tangent, if I want to draw it, it becomes the line parallel to the y-axis. And any point that you intersect with the tangent line, it gives you the value of the tangent. Then you see that if alpha gives you the value which is positive 1 for the tangent, then another angle which is minus alpha gives you the symmetric line which is going to be minus the same value of the tangent of the alpha. Then it means that if the tangent of pi over 4 becomes 1, then the tangent of minus pi over 4, it gives you minus 1. Then you can come here to write that x becomes minus pi over 4 plus k times pi. The k times pi, essentially, that's what we add in order to make infinite number of the solutions because of the periodic behavior of the trigonometric function. But for this one, it's going to be the tangent kp, because 2 pi is for sine and cosine, as you learned it before, and pi is for tangent and cotangent. And that's going to be another set of solution. Guys, any questions?
No.
Philip and Ferris? Maybe you stepped away, but then as a result, I compacted this and I write this, that the second solution is going to be x equals to minus pi over 4 plus k pi. Then we have two sets of solutions. The first set is going to be pi over 4 plus k pi. The second solution is going to be minus pi over 4 plus k phi. Why? Because the tangent squared of the x equals to 1 was decomposed into two different equations. Guys, please spend 2 minutes to see that if you can find any questions. Does everything make sense? The solutions that we had for both equations?
Yes.
Thanks, Rose. How about Philip and Ferris?
No.
Ferris, are you okay?
Yes.
Awesome. But please make sure that you watch the video and the things which we have done in the past. These things are I'm sure it's going to be very easy for you. But please remember, anytime then you review that, and when you have some problems, please don't hesitate to send me email or message on the Schoology then, okay?
Okay.
Awesome. And also Ferris and Philip, please don't hesitate to ask me questions. And talking about, I should say we are done today with these trigonometric equations. Tomorrow we have more examples in case if you have some problems, then we are going to talk about the presentations that you're going to have. Guys, I reduced the number of the presentations of your class to only one presentation. You do not need to just have 2 presentations, okay? You can either choose between Hodgkin-Huxley, or either you can, Hodgkin-Huxley is very, very difficult, I know. You do not need to do that, but at the same time, you can just do the radioactive decay, which is very easy. It's part of the lessons that we had, the exponential decays, and talk about its applications into the cancer therapy. I checked the resources. It's very easy. You can find one single equation, talk about that, and read something about, let's say, ionizing radiations for the cancer therapy. It becomes very easy then. Then you need to only do one project. There is no need to do 2 projects then. Maybe it was too much. Okay, and Rose, which one do you prefer to do? Hodgkin-Huxley or radioactive?
Hodgkin-Huxley.
It's good for you, huh? You also did your writing on that thing.
Yes.
Awesome. When do you want to do that?
When? Next week.
Next week is good.
Yes.
You were supposed to have what day of the next week? You want to do that on Tuesday after long weekend?
Okay.
Or do you need more time?
I think that's fine.
That's fine. Okay. I think Tuesday it's going to be for Rose. And how about Philip and Ferris? Philip is gone. Ferris, are you there?
Yes.
Okay. When do you think that it's going to be fine for you to just present your work? Radioactive decay in cancer therapy. It's only one single equation. If you Google it, there is only one single equation, and you need to read from somewhere about its nature and what is a cancer therapy for it.
Let me think. Maybe
Is it good next Friday? You have one more week.
Yeah, that's okay. I think maybe like Thursday is fine. I think.
Oh, Thursday next week, huh?
Yeah, Thursday or Wednesday. I think I can be ready for it.
Fantastic. That's great. That's great news. Then I think Thursday we pick up Thursday, huh?
Yes.
Thursday.
Oh, I mean next, not this one.
Yeah, no, of course. Yes, sure. Then because we have a long time, we have a long break. You can start from Tuesday. Then you have Saturday, Sunday, Monday to catch up with it. I'm gonna have less. You have only one homework for this weekend, which you have probably have done it so far. Then you have enough time to work on your presentation. Then the good news is that we do not have to have 2 presentations for this term. You have only one. Then you do one, and things becomes easy. It's good, huh?
Good.
Awesome. Then guys, please remember, please review on the things that we did today. And if you have any questions, catch up with me either by email or Schoology or tomorrow morning in the class. Okay, everyone?
Okay.
Awesome. Then guys, enjoy the rest of the day. Enjoy the nice weather and happy studying. I see you all tomorrow then. Bye, Faris, and bye, Rose.
Bye. See you tomorrow.
See you tomorrow. Enjoy the day. Take care, everyone.